Okay, so let's start our introduction to our first paper. This paper itself is not long, but as this is the first time for you to read a paper in this field, I'm going to slow down and use two lectures, lecture 3.2 and 3.3 to introduce the paper. Yeah, in this lecture, what I want to do is to give you the motivation for the thing it studies, and then give you one numerical example to convert idea to you, and then introduce the model. In the next lecture, we're going to do those mathematical derivations and get those messages he wants to deliver. Okay, so this paper is written by Pasternack in 1985. Yeah, in this paper, a common practice adapted in distribution channels is studied. This is called the return contract or buyback contracts. Okay. When we observe a practice, typically we ask the following questions: why do we want to use this practice, and what is the benefit for using this kind of practice? Okay, and when we are talking about benefits, we want to know what are those underlying forces for we to get those benefits. Yeah. So we're going to repeat these kind of questions many times in this semester when we see different studies. Okay, as we can see, this study discuss this particular thing called return contracts. We're going to see that what's that, and in this lecture, what our plan is to illustrate the main insight with a simplified model. If you are going to read the paper, the whole paper is centered with a model, and that model I won't say is very complicated, but here we're going to use an even simpler model. Okay, we're going to ignore some minor parts in that model, and we're going to use the simplest model I can find. That is enough to tell you the main story. Okay, and to make your understanding easier, I'm going to use a slightly different notation from the paper. Okay, so when you change from this video to the papers, you may need to do some conversion in your mind about notations. Yeah, but I believe the way we use in this video will make you easier to understand the idea and the derivations in the paper. And for most of the papers we're going to discuss in this semester, we will focus on this method. We're going to introduce the paper with a simpler model in the video, and then I hope that will make you easier to read the paper entirely. Okay, so we will start with the motivation. Why do we want to study that? And then I'll give you an example that you cannot find in the paper, and that example can help you to get some idea about the problem. And finally, we will introduce the model and then finish this lecture. Okay, so in many distribution channels, manufacturer would sign a wholesale contract with the retailer. That means I give you one product, you give me $5. I give you two products, you give me $10. Each product is sold at a wholesale price. Okay, this is the case that you have observed in the indirect news vendor problem, and we know there are something wrong there. What's wrong? What's wrong is that the inventory level or order quantity, supply quantity, production quantity, is too low. The retailer will not order the optimal quantity for the system. Okay, we know the inventory level is optimal for the retailer, but it is actually too low for the system. So probably you want to ask why the retailer would order an inefficiently low quantity. Here we say the quantity is inefficient because it is too low. The reason is here. So first we know the demand is uncertain. Okay, and in the particular setting with wholesale price contract, the retailer takes all the risks and the manufacturer is risk-free. Okay, if you remind yourself about the setting, the retailer must somehow forecast the uncertain demand and then place an order. when the manufacturer sees the order, the manufacturer makes the production, and he needs to produce just exactly the amount the retailer orders. So that means the manufacturer has no risk about making production because all the products he makes will be purchased by the retailer. So that's why we say the retailer takes all the risks and the manufacturer is risk-free. Okay, so when we know the retailer takes all the risks, what's going to happen? When the unit cost becomes higher, for example, from the unit cost to the wholesale price, overstocking will become more expensive, more harmful, and the retailer in this case must lower the inventory level. Because there is such a risk, and because the cost becomes higher, the retailer, to best manage those risks, the retailer must lower the inventory level. So, knowing about that, how may we induce the retailer to order more? We know one possibility is to reduce the wholesale price, but we know that's not going to be possible because this wholesale price has been calculated as the optimal wholesale price for the manufacturer. If you ask the manufacturer to reduce the wholesale price, he is not going to agree for that. So we're going to discuss another way which is more practical. It's for the manufacturer to somehow share the risk. Okay. As a manufacturer, I know the retailer is now taking all the risk. I, as a manufacturer, I somehow try to share some risk with you. And I hope that's going to encourage you to order more. That's the whole idea about this, sharing the risk. So how may we share risk? One way is to use the return contract or buyback contract. We say this is a risk-sharing mechanism. So why? The contract works in the following way. When the products are not all sold at the retailer side, the retailer is allowed to return, maybe all of them or part of them, return those unsold products to the manufacturer and get some credits from the manufacturer. That means if I have 10 units left, for example, and I am allowed to return all of them, I'm going to return those 10 units to the manufacturer, and the manufacturer is going to pay me something as the credit or buyback price. Okay, so knowing about that, what's included in a return contract? There are three contractual terms or contractual arguments. First is again the wholesale price. We still have the wholesale price. And then we must specify R as the buyback price or return credits. This is the amount of dollars the manufacturer pays to the retailer when the retailer returns one unsold product to the manufacturer. Okay, and finally we allow the flexibility for the manufacturer to specify how many or what's the proportion of unsold products that can be returned to the manufacturer. So R is the percentage of products that can be returned. For example, if R is 80%, then when the retailer buys 100 units, then at most 80 units can be returned to the manufacturer. With this, we know there may be several different ways, different kinds of return contracts. The first one is the most generous one, for return with 4 credits. That means R is 1 and small r is W. You are allowed to return everything. And once you return something, I'm going to give you what you paid to me. Okay, that's for return with 4 credits. Or you may want to implement for return with partial credits. Yeah, indeed, you can return anything to me, but the credits you may get is lower than the wholesale price you paid. Or a partial return with 4 credits, R is less than 1, or a partial return with partial credit, R is less than 1, and the small r is less than small w. So one thing to remind you, or I want to tell you, is that in practice, the manufacturer may pay the retailer and do not ask the retailer to ship those physical products back. Why do we have this situation? Why manufacturer is so generous that he is giving the retailer free money without asking for any goods? The reason is that all the manufacturer wants is to use those return credits to motivate the retailer to order more. That's the whole reason. The manufacturer itself does not care about those physical goods. Please do not return those products to me because I don't want to spend any money to dispose those products. Okay, that may be something in the manufacturer's mind. So the key idea here is that for return contracts to work, what's important is for the manufacturer to share the risk with the retailer. The point is not on those physical goods. So return contracts, there must be some good news and bad news. Let's start with bad news. So first, certainly, a return contract is harder to decide because now there are three arguments there. And also, if you decide a really bad return contract, then that may be even worse than a good wholesale contract. Yeah, I guess that's somewhat intuitive. But there are also some good news. So first, a wholesale contract is actually a return contract, or we may say a wholesale contract is a special return contract. Given any wholesale contract, all you need to do is to choose small r to be 0, and that's going to give you an equivalent return contract, right? And that directly tells us that it is very easy, or it is quite hopeful for a return contract to beat or to dominate a wholesale contract. So that's why intuitively we have the other two good news. A good return contract can be win-win. Here, win-win means a good return contract may make both the manufacturer and retailer earn more in expectation. And even a well-designed return contract can be efficient. That means inducing the retailer to order the quantity that can maximize the total expected profit. That means can make the pie as large as the integrated case. Okay, so that's the power of return contract. Before we jump into the analytical model to show you those good news are true, let's first get the idea with a numerical example. So suppose we have a channel. There is a manufacturer, we call it she, and there is a retailer, we call it he. Somehow one is girl, one is boy, and that's not a big deal. And the unit production cost is $10 for a product. The unit retail price is fixed at $50, and in this example, the random demand is assumed to follow a uniform distribution between 0 and 100. So as a benchmark, even though we know this is not going to happen, let's first analyze the integrated case to find the efficient inventory level, because that's going to be our benchmark for comparing and for finding the performance of our contracts. So let's assume QT star is the efficient inventory level, T for total profits, okay? QT star. So if we want to find a QT star to maximize the expected system profit, we have solved this problem in the past. This is nothing but a usual news vendor problem. The left hand side here is the, let me write it down. This is nothing but capital F of Q star of T in this problem. And the right hand side is just 1 minus the critical ratio. We know this formula is used in general to solve news vendor problems. We get 80 as the efficient inventory level. Okay, in this case, the expected system profit, something we want to maximize. If we first find it as a function of Q, it can be calculated like this: unit price times the two possible cases to sell products. If the if the demand is between 0 and Q, we're going to sell the demand quantity. If the demand is higher than Q, we're going to sell the inventory quantity. Okay, this is the expected sales we have, times 50 is the expected sales revenue, minus 10Q. This is the definitely we need to pay this amount to produce these products. After some derivations, you can show, and I expect you to derive that by yourself. this quadratic function is the expected system profit. If we plug in 80 into this function, we're going to see that the optimal system profit is $1,600. Okay, now we have that. Let's start to analyze the decentralized case. So under the wholesale contract, we have the indirect news vendor problem. And again, we have solved this problem in the past. We know in equilibrium, the manufacturer is going to charge $30, which is the combination of the fixed retail price and the fixed production cost. Given this wholesale price, the retailer is going to order 40 units. And if you still remember what we did in class, now this is indeed what we have shown. The retailer will order just 1/2 of the system optimal quantity. Anyway, given this, the retailer's expected profit can still be calculated as a function of Q. Here the expression is almost the same. The only difference is that here this number becomes 30. From centralized to decentralized system, the retailer is in some sense facing a higher cost because the cost is now the wholesale price, which is 30 instead of 10. And then you may still solve the problem. You get this quadratic function as the retailer's expected profit. If we plug in those numbers, the retailer's expected profit is only 400. The manufacturer's expected profit is 800, and the expected system profit, sum of these two, $1,200, that's smaller than the system optimal expected profit. Okay, this is how another way for us to see that wholesale contract is not system optimal, because eventually they together earn a smaller, eventually these two firms are creating a smaller pie than what they may do in an integrated case. Okay, that's the wholesale contract. So we know the wholesale contract is not very good. So let's try to see how may we improve this wholesale contract. Let's study the first proposal, the first return contract. So one guy may say, how about this? The wholesale price is fixed and the return credit now somehow we may say goes up from 0 to 5. Previously you do not allow return, but now how about you allow a $5 per unit return policy? Okay, and let's assume you are generous. You are allowing the retailer to return anything left. Okay, so when you see this, at the first moment you may find this contract is definitely more generous to the previous wholesale contract, right? Now the only difference is that there is a return credit, okay, from 0 to 5, and the percentage of allowed return is 1. The manufacturer did not charge more. Instead, the manufacturer is offering return. So you may think the retailer would be happy, but the manufacturer would feel unhappy. Let's see whether this is true. In this case, the retailer's expected profit needs to be calculated again with a new term. So we want to show it, the retailer's expected profit, as a function of Q. Let's denote this guy as a pi r with a superscript 1 to denote what's going on under the first return contract. So we can see that there is still one term very similar. This is what the retailer may get for selling products to end consumers. Either all the products, all the demands are fulfilled, or there is stock out. Only the inventory level are sold. Okay, and this is the unit price. There is also one term that is owed. This is the cost paid to the manufacturer. The only thing that is new is here. Okay, this is what the retailer may get by under this return contract. Now, if the demand is not as high as Q, there will be some leftover. The amount of leftover is capital Q minus X, and for each unit of that, the retailer is compensated by $5. This part is what happened under the return contract, what's new under the return contract, and it translates to this new quadratic term. And you may verify that after all you will get this. The retailer's quantity will get higher. The retailer will now order 44.444 blah blah blah, which is higher than 40. The retailer is going to order more. Definitely that's true, because now the retailer feels more confident about having overstock, because in that case the retailer can return those products to the manufacturer and get some compensation, right? So as a retailer, definitely we will order more. So under all those calculations, the retailer's expected profit can also be found as 444 whatever, yeah, and this is again higher than previously 400. The manufacturer's expected profit, now this is expected profit because now the manufacturer is also facing some risk. Okay, the manufacturer's expected profit has two parts. The first part is, again, this is the quantity, the sales quantity. This is the wholesale price. This is what he may get by selling the products. And now there's another term. This term comes from here. Okay? In expectation, the manufacturer needs to pay this amount to the retailer as the return credit. Okay. But surprisingly, after all the calculation, you can show that the manufacturer also earns more. The manufacturer now can earn $839, which is higher than 800 in the original setting. And of course, the expected system profit also goes up. So you can see that under this return contract, the retailer orders more, and both the two firms are happier than in the wholesale contract. Okay? So if that's true, then you probably want to ask, what if the manufacturer becomes even more generous? What if the return credit becomes 10? So you may calculate all of them because you can do calculus, and now you can see, indeed, the quantity becomes even higher, now becomes 50. You may plug in these numbers into everywhere. The retailer now earns even more, 500. The manufacturer also become happier. Now it's 875. So when the manufacturer becomes more generous, both firms earns more in expectation. It's just one thing. The expected system profit, even though it's higher than 1,200, is still less than 1,600. Okay, it's still not as good as the integrated case. So after all of these analysis, let's summarize their performance in the following table. So we can see that wholesale price are always fixed the same, capital R in some sense is the same, but small r, the return credits, may be 0 in the wholesale price contract, 5 or 10. And we can see that when R goes up, quantity goes up, both firms earns more, but none of them is system optimal. So you will naturally have the following question, I hope. For example, when we keep increasing R, will Q keep increasing? When we increase R further, will we always make these two firms happier? Will a more generous manufacturer always make them both to be more profitable? Okay? And is there any possibility for us to achieve system optimality to induce the retailer to order as many as the system optimal quantity. And in that case, naturally, we will make their total profits equal to 1,600. And actually, we can have even more questions. So, what if the wholesale price is not 30? No one says under a return contract we need to stick to 30 as the wholesale price. Maybe we may change it to another number, and that's going to make our situation better. Okay? Or what if R is less than 1? We may choose to do partial return. Will that make things better or worse? And finally, what if the demand is not uniform? What if the demand is something we just we know what's that, but it's so ugly? Okay. In general, under general demand functions, what will be our results? Do we still have all the results we have found in this example? For example, we showed that both firms can benefit from a wholesale price from a return contract. Will that still be true when the demand is not uniform? We have no idea, right? So that's why we need analytical models. So the main question in one sentence is that when may we achieve channel coordination? And here channel coordination means under decentralization, players make system optimal decision. Okay, the retailer orders 80 units. That's called channel coordination. And we need a general analytical model to deliver insights. That's why I'm going to introduce the general model to you. Okay, we're going to consider a manufacturer-retailer relationship in an indirect channel, two players. The product is assumed to be perishable, and that's why we consider a single period problem with demand uncertainty. The production is under make to order, and that means the manufacturer can produce products after he gets the production order. And the retailer is a news vendor. Price is fixed, and he needs to make the order quantity decision. We use the following notations. Some of them has been shown to you. We're going to use C as the unit production cost. Small w, small r, and capital R are those terms inside a return contract. Capital Q is the order quantity, and the capital F and small f are the CDF and the PDF of the random demand. There are some natural assumptions. First, you know the wholesale price is going to be within C and P because the manufacturer wants to make some money and because the retailer wants to make some money. Okay? We are going to assume that the return credit cannot be higher than the wholesale price. And this is something we really need, because if R is going to be greater than W, as a retailer, what will you do? You're going to order 1 million units, because after you pay the wholesale price, you can sell all of them back and get something more. Okay, so that's why we need the return credits to be less than or equal to the wholesale the wholesale price. And finally, we assume demand are non-negative. Okay, so now let's read what's really difficult. This is the retailer's utility function, the retailer's expected profit. Here we have 4 terms. The first term is nothing but the certain payments paid to the manufacturer. Okay, so that's one thing. And then there are 3 different terms. Let's look at them one by one. For the first one, it's saying that what you may get when the demand is below 1 minus R times Q. So let's use a graph to denote that. Suppose as a retailer I order Q units, and I know there is a quantity 1 minus R times Q. I know this because this part is the this part can be returned. Okay, So now, if the demand is smaller than 1 minus R times Q, somewhere here, what will be my earning? My earning will be first, for this part, I'm going to get P dollar for each unit sold to the end consumers. For the second part, this part are unsold, but this part generates no earning to me because I am not allowed to return this part to the manufacturer. And then finally, this part is allowed, and this part, for each part here, I can generate small r as my return credits. Okay, so that's why in the first part you have x times p. X is the sales quantity, and then capital R times Q is the return quantity, times R is the return credits you get. That's how you get your first term. Okay. For the second term is the situation that your demand is above 1 minus R times Q, but is still lower than capital Q. So the demand is somewhere here. In this case, for all of them here, you are going to get P because you sold all of them. But for all the remaining, now you can return all the remaining because they are all allowed to be returned. And that's how you get Q minus X as the return quantity. Okay, so that's good. And finally, there is something that is somewhat easier. When the demand is higher than capital Q, we go back to the usual news vendor situation. You're going to sell Q units, and there is nothing left. You cannot return anything, and all of them generate P per dollar. Whew. So yeah, that's how we get the retailer's expected profit function as the sum of everything here. The manufacturer's expected profit can also be explained in the following way. So first, he has this original term for getting sales to the retailer. But now there are two more terms that come from the return fact. So the first term here, as you may see, comes from the first possibility. And the second term here comes from the second possibility. In either case, the manufacturer is going to take some returns from the retailer, and the manufacturer needs to pay something to the retailer. So the whole parts, the two terms here, are the expected return credits the manufacturer pays to the retailer. If you sum both of them, you're going to get the expected system profit as this, and as you expect, W will disappear, small r will disappear, capital R will disappear, because W, R, and R are just something inside the system. But when we are asking for system performance, system expected profit, in those terms will not appear. Okay, finally, how do we play the game? First, a return contract is signed by the two parties. Here we do not specify how do they make these terms. Okay, we do not assume how may they do negotiation, do bargaining, or whatever. We only want to analyze what will happen after there is a return contract. Okay, so they first sign the contract, and then the retailer places an order. Okay, and this is place is an order, and then the manufacturer will produce this and ships the product to the retailer. Again, the manufacturer's production environment has no uncertainty. And after all of this, the sales season is going to start, and the demand will realize. And then the allowed unsold products, if there is any, will be returned to the manufacturer, and the manufacturer pays the return credits. Okay, that's how they play this game. So now we have the model, we have the utility functions, we have the timing. In the next lecture, we're going to tell you how to solve this game.